So friends, we are there on the fifth lecture of 7th week, and that is Prognostics and Health Management, a systems approach. Okay. In this lecture, we'll see how diagnostics can be implemented in machine learning. We'll not be exactly discussing machine learning, but a sort of connection between diagnostics and machine learning. So let me introduce first. Diagnostics and prognostics both can be done online or offline. That we have shown and discussed there actually. And objective is to know or detect any deviation from the normal operation actually. So in that sense, diagnostics is a present situation, what is going on and what will happen, but the prognostics is predicting the future. So there is one difference. Okay, and they have overlapping actually. Data-driven machine learning techniques are emerging tool for, because physics of failure on the contrary, they require a lot of scientific depth into failure. Each failure has got its own characteristic. So machine learning and data-driven technique, they are basically tracking in time and trying to tell what is going on, and that looks much better an option. Prognostics using physics-based approach can be useful for reducing the uncertainty. That means one module which was predicting based on data, now other one physics based. So if they join together and they can reduce the uncertainty in declaring the results, that will be a good idea. But for that, physics for failure approach have to come to real-time situation, especially a lot of electronics have been done. So I think electronics is going to be the first area where POF working with the data-driven approach. And for complex system, the domain is very vast. So probably the in complex system, signals are being monitored. So use the process parameter or signatures which are there in the control room for prognostics, number one. And number two, go for data-driven approach. That means at local level in the area, are the signal coming on the health of the machines also. And in that case, the fault tree, event tree, knowledge is, part knowledge is available. It has to be further expanded. We have, as I mentioned earlier, expert system based approach. So fault tree, event tree can directly translate into rule based approach, and wherever quantified rules or quality rules are not available, linguistic informations are vague, the situations are there, even fuzzy approach can do a good job. Sign digraph, though it did not form part of my lecture, but then during while discussing some example, I will definitely discuss this. And then Neo's base classifier. It is a classifying approach where, and here I have done in this lecture, I have done this, use of this approach, Neo's base approach for classifier, that is yes or no response variable for a common cause failure mechanism. And since there was some example available in generic source, I have adopted that thing for our common cause failure analysis. So now major elements of diagnostic algorithm. So one is identifying the objective and scope, then domain expert. I am repeatedly talking about domain experts involvement into the to elicit the knowledge and the model is a key to success of diagnostics, the way it was there for even prognostics also. And then we have to have a regime for data pre-processing, machine learning. We have to select proper machine. That is the machine learning approach. It could be ANN, it could be statistical approach, but the results define what kind of approach we are going to use. And for that, a lot of iteration or simulations are required. Especially for rule-based approach, there is a strategy called inference engine. If X is equal to Y, Y is equal to Z, then the consequence. So for making it working in a machine learning model requires an inference engine approach. So we should have a proper inference engine approach, and then training of machine learning approach. Maybe if we have a data set of X, so 0.8x we can use for training, and 0.2x we can use it for recall test, because we have to validate the model actually. And apart from this, some new vectors have to be brought, and unless until we put it in the use, we will not know whether our training is complete or not. So it is like a human keeps learning all through his life in the operational ecosystem. Machine also has opportunity because new event has come. So if it is not able to match onto our vector module, then new event should be recorded, and the machine learning algorithm should ask whether you want to train this algorithm. If we train it, it becomes part of our vectors, trained vectors. So how the framework works, and we are talking about the supervised learning only. So first, as we mentioned in the previous slide, scope and objective. Then just to underline the point, domain expert and machine learning team, they should work together for data pre-processing and feature extraction. And domain expert should be on the same page with the machine learning expert. Okay, whatever features we are extracting, they are relevant and they can be fruitfully utilized. And then preparation of vectors, that means labels. So for every vector there will be a label, and if this is ready, then we have a machine learning algorithm. Okay, training goes on actually. So once you have a trained ML, then test vector should be subjected, and finally we have the trained machine learning diagnostic framework. These steps are important to have a robust model of diagnostics in a plant, and this should be generic to the extent possible. That means it should be so much its applicability it should be for electronics component, mechanical components, civil component. So the model should be generic and available for rule-based approach. In fact, it should accommodate different techniques also. So this machine learning algorithm, it should be embedding the most of the machine learning tools and methods which are there. And here we can use an inference strategy to use this tool, and training can be performed, and trained model is available here. And finally, it is validated and certified to be used in the field. So with this, now let us see, we are talking about fault tree, event tree and all that, So how the fault tree, event tree we know. Top event, probably if you may not know, this event is called top event, this is called OR gate, these are the links, and these are called intermediate event, because finally when we start developing, we will have to use this tool like a domain expert, and then this is OR gate. So how it translates, A or B or C happens, then intermediate event occurs. Okay, but this is OR gate, but AND gate, D and E should happen to activate this intermediate event. Okay, so now and finally it will go to the, because it is OR gate, any one of the thing get activated, it will go to the top. So top gets activated. So now we are talking in terms of machine learning and processing the data. So basic event, OR gate and AND gate, just for the understanding purpose. And so once you arrive here, it can be that goal found, technique. So that means machine learning algorithm will stop at this point. If we connect this particular node to an event tree, then it will try to understand the consequences also. That means this input will go to the event tree top, and there we are, event we have identified, but and these root causes also we have identified. So now if a consequence vector, that means what is the level of risk or consequences that can be done in the event tree. So let us see one example here. We have this diesel generator, okay, and this diesel generator can fail because of these are the modes of failure, So we see in our FME, DA or anyone, mode of failure is important. So mechanical mode, actuation system failure, loop while failure, starting signal failure, control and protection system, lubile has come twice. Okay, so this we can ignore. And now for mechanical failure, it could be bearing failure, that is diesel generator bearing failure, crankshaft failure, piston failure, and cylinder failure. Now, I have indicated a basic event here. That means I do not want to go down, but bearing failure, I'll go down to further details, inner case, outer case. If it is a, of course, roller bearing, if it is a hydrodynamic bearing, then I'll have one shaft running under fluid, and there is a fluid is separating the stationary part with the dynamic part. So lubrication will come into the picture there. So the details will depend on what kind of component or interfaces coming that lead to failure. Crankshaft failure, then piston ring failure. These are the components they see because they are reciprocating components, and they frictions are reduced by lube oil, lubricating oil, or oil which is used for so. But then if the oil quality is not good, piston ring failure occurs. Cylinder failures, they are more rugged compared to anything. So normally you don't see cylinder failure unless until some catastrophic phenomena has happened. Similarly, now you see here, these are OR. Any one of them fail, then we have diesel failure, because everywhere it is connecting through OR gate. But here you see actuation system. There are two systems which are there to start a diesel generator: air start, compressed air start, or electrical motor start. So these two are there. Unless until both fails, this will not go on top. Okay. So if suppose air start has failed, the electric start is available and system is success, and the event will remain here. And that is the advantage of redundancy. Here there is a not redundancy, there is a diversity. The air start, and so this is much higher level of redundancy, because similar component they are redundant, but different component or system working on different principles, air systems, and they are truly diverse systems, and their probability of failure is less, because their dependence is also not there on each one of. Now starting signal, for starting this we require a starting signal. So under voltage signal, if it is not working, relay is not working, control signal, relay signal, and solenoid. Solenoid is the final actuation device which will put the things on this. So starting signal, diesel starting signal I should say, control protection system. These events I have not developed, because for understanding we had this lubile, no lubile, fuel pump, and oil. Don't you think it has provided a very elegant mechanism for developing our diagnostics? Components into intermediate level, and then finally basic component level. So with this itself you can create your rule base, okay, and production rules for diesel generator. And if you implement during a situation when class 4 power or offside power failure has occurred, one diesel has not come, and this particular format was available in an expert system which is supporting the plant in charge or shift engineer, automatically one of the failed component will come on top. Diesel generator has failed because of starting air problem. So easy to know. Then I will focus on other one is available. Yeah, and you will find that if it is not started, both have failed. Why both the things have failed? Is there any common cause other than that? So these are the independent causes: relay, solenoid. Solenoid has not got actuated. Coil must have got burned. So those things further we can develop, and maybe this same fault tree might run into 20-25 pages, covering all the component to their root level actually. Okay. So now fault tree, event tree we have seen. There is one special case I am discussing here, that is Bayesian theorem. Bayesian theorem provides a very good diagnostic approach, and it is basically trying to, in probabilistic way, we are trying to understand whether the one mechanism is there or not there, how it is there. So we know that Bayesian theorem has got a priori evidence, and priori means already available information. And so what happens if we do not have data, then limited evidences, then priori, which is available in the, let us say, diesel generator failure probability, it is there in the generic domain. I have some evidences collected for 1 year. So I will use Bayesian approach to combine these two sources, to provide the estimate of diesel generator. So here this algorithm is like this: probability of A into B. We all know that if they are dependent event, then probability of, suppose they are independent event, then probability of A into B, that is A intersection B, is equal to probability of A intersection probability of B. But if they are dependent event, then it can be written as probability of A intersection B is equal to probability of A into probability of B given A. That means we have some knowledge of A also. At the same time, this same thing can be written like this also: probability of B intersection probability of into probability of A given B. If we solve this thing, for probability of B given A is equal to probability of B, probability of A given B, and probability of A, because I am just reorganizing the terms here. So this is known as Bayes theorem, and this theorem, whether it is updating the reliability data or trying to solve a problem where two sources of information and we want to reduce the uncertainty, even it is used for estimating the uncertainty also. So let us see one example here. I have one electronic system, okay, and I want to analyze that thing. And what are the factors which affect the quality of the electronic board performance? Okay, so I have and I know which are the factors they might adversely affect the electronic board operation. So I have this quality military grade component. That means the component fabrication itself has followed some standard method. So they are the highest quality. Then there could be low quality component. That means from local manufacturer we have got it. So one is middle grade, one is low grade component, and one is medium grade component. Why medium grade component? Because this component we bought from the open market, but we subjected them for qualified testing. Okay, sometimes it could be even mill testing we have subjected. So it is a medium grade, and that is quite correct also, that we have done our own verification and all that. But definitely it will not be a mill grade component, and it will not be lowest component, so medium. So these are the categories of its quality level that we can give, and depends on what kind of thing we use. So this is data table for this particular. Now electronics get affected by, we know that, temperature, okay, humidity, and human factor. Human factor maybe in calibration, installation, and repeated in-out maintenance, so it gets affected. Now let us see, now I think these abbreviations I have not given, so please listen very carefully. It is ground benign, the temperature, that means the instrumentation rake where the electronic board was installed, it is ground benign. Ground benign means 22 degrees centigrade temperature and humidity 55%. So that is ground benign, and that is the ideal condition for electronics to operate. So other one is ground benign temperature high. That means it was not 22, it was higher. Okay, so I have put H there. Okay, and then ground benign temperature medium I have put here. So that means it was not ground benign, but there are some variations. And with that I have made some qualifier for accounting for temperature increase or decrease, not being either being ground benign or low or high. Low doesn't. And humidity also, ground benign humidity is, you know, that 55% ground benign condition. But if it is H means high humidity, 70%, 80%, definitely component. And electronics, what is lubrication for bearing, lubrication quality for bearing, for electronics, it is temperature and humidity. If we are not able to maintain proper temperature and humidity, then the electronics failure will be more frequent actually. Then ground benign high, humidity, H stands for humidity here, and another H stands for high. Please listen to me very carefully, because all abbreviations I have not given. So H stands for high also, H stands for humidity, basically ground benign humidity. It says humidity is 55%, which is correct, required humidity is there. And then one more factor is human factor. Human factor can induce in the test, maintenance, operation, or even qualification some error. So if we have experienced staff, we feel it's okay. If experience is low, one more barrier. If it is a skilled, that means in between that, so we have that. And last column, it is called response column. Okay, response column is common cause factor judgment. You can imagine that I collected this data from 15 experts or 15 industry, and they have given their opinion why common cause failure probability will be no or yes for which combination. So now you see, I have got all the information with me, and now I want to understand the probability of common cause failure. No means no common cause failure will occur, or yes means there is a probability of yes, there is a probability. We have to read this statement also. When I say yes as a response factor, yes, this is common cause failure will be there, and no common cause failure will be there. So for us, no is important. We do not want common cause failure. So now let us go ahead and try to see how we have modeled this problem. But now we go to the base theorem we understood. Now let us go to what is B1. See, now we have common cause failure of electronic complex critical parameter. Common cause is rare event. Still, the past data or sets record shows as follows. Consider the classification of A in the class label. That means A is showing you the label, that is response factor, and B is the matrix that we are trying to, like we said, I chose the vector 5. So B indicates the 4 parameter: commercial, ground benign T, ground benign H, humidity, and experience. And A is the response variable. Last column we saw that. So data type, and then assumptions are features are independent, equally significant for common cause and data sets considered in the. So independent and equally applicable. That is an assumption. That will be using this term for simplifying our model. How we do that actually. So now if I convert this whole problem into my problem is B is a class label yes or no. Okay, B is a class and labels are yes or no. Okay. Now A is equal to A1, A2, there are factors here for A. Or for example 5, we have medium, ground benign T, same thing I am repeating here. Now for PA, we have these possibilities: probability of A given B, probability of A2 given B, probability of A3 given B, and this is how we are trying to estimate the priori probability B. Okay. So, but probability B for A1, A2, A3, A4. Okay. Now, probability of B is equal to probability of B, probability of AI given B for this I. They are all I actually, and probability of A divided by. So, the Bayesian algorithm. Now, PBAI is posteriori probability. That means this is our posteriori probability. Probability B priori probability. Okay, and probability A evidence or likelihood estimate that we have with us. Okay. So the final theorem is B cap, that is probability of B we are trying to see, B header, maximum likelihood estimator for our problem. So probability Y into pi, I is equal to 1 to n, that means all multiplication of AI thing, whatever we have, the equation is called Naive classifier. Okay. And now if I translate it into the problem, for my quality matrix, I have common cause failure yes. How many yes are there? Mill rate ka 1, medium 2, and low 3. So total 6 yes are there. Similarly, probability of yes 1 by 6, 2 by 6, 3 by 6, straightforward 100%. Common cause failure no, 4, medium 4, and 2, so 10. So now we have probability of no is equal to 4 by 10, 4 by 10, 2 by 10, and 100%. So if I add all, it will become 100%. Now example input, we have A medium same vector, that is vector 5 I have chosen here. Now probability of yes is equal to 6 upon 16. Okay, because there were so many yes that we counted actually, and probability of no is 10 out of. That means in the last column, total number of yes and total number of no. So that we have over here, and we estimated this probability. Now let us say some feature we take, quality medium 2 by 6, 5 by 6, temperature this thing, and we came to this probability, yes ka probability and no ka probability. Now we will bring in that conditional element of this. So common cause failure yes is nothing but individual 2 by 3, 3 by 6 and 6 by 16, that we estimated. Okay. Probability of yes per year, because I am trying to predict that per year what was the observation of each individual that data came from. For no per year, this is we got yes ke liye. Now for no also we got 0.034. So that means probability of yes is equal to 0.026, which came from here, and this is summation, normalization we have done. So 0.44. Probability of no common cause failure will be there 0.57. So this is a higher probability. We will use this thing. So no probability of failure is higher. Okay. Analysis predict the reference failure. So for common cause failure, based on the expert elucidation technique, correcting opinions, and we try to assess what was the probability. Of course 0.57 is high, but this was an example for demonstration. Okay. Normally I will tell you, common cause failure maximum 0.1, it is now, there is a consensus and it is less than that. But this method has less to do with the quantification, but more to do with how you can arrive. This is an alternate mechanism which is available other than the statistical or empirical methods that have been given in the books and all that. And for this book, I have used this example of naive-based approach. This particular website and McPhee, HTTPS and all, and I think I should thank them, because this was a beautiful example that was given, which I could adopt it for my common cause failure analysis for presenting it to you, because otherwise we think common cause failure contribution involves a lot of complication, lot of data is not available. International organizations are working on that. But if we use like fuzzy logic, an important input, I think it will be a great deal that we have.